In this video, we'll finish up section 3.1 with one last application. This one, I feel like our curriculum just gives lip service to because it gives us this equation and we plug it in and it just becomes a diffie-q. We're not really thinking about the circuits and making them complicated. Okay, so series circuits, a series circuit containing only a resistor and an inductor. Kirchhoff's, I'm guessing that's, or Kirchhoff maybe. Second law states that the sum of voltage drops across the inductor and the voltage drop across the resistor is the same as the impressed voltage E of t on the circuit. So wherever that came from theory-wise led us to this diffie-q that we have there. This is a first order linear diffie-q. Sometimes they're separable as well. L and R are the inductance and resistance respectively. So we just need to know those if they ask for them. I'm not going to do that. If I give this kind of problem on assessment, this kind of information would be given to you. I don't expect you to memorize this type of thing. The voltage drop across the capacitor with, I can't say this word, so I'm just going to not, is given by Q of t over C, where Q is the charge of the capacitor. I feel I'm just going to say it wrong, so I'm not even going to try. Hence, for the series circuit shown in figure 3.1.9, okay, I've done a little bit of work in these. Mine doesn't go very far. I just know that comes from, we can do systems with that kind of thing. But my background's in math, not in electricity or even physics, but pure mathematics. So they give us this, we have this new diffie-q given those variables, and then, but the current I and charge Q are related. Thought that was interesting that the current is actually just the derivative of our charge in this case, which gives us a new diffie-q. These are the same. They just replace the I with dq dt because it takes, since they're related like that, it takes this equation here and turns it into a diffie-q. So we're going to work in the next two examples. We're going to use one of these and then the other and plug them into solve. Like I said, this is, I feel like just doing lip service towards circuits, not really teaching much. And I'm okay with that. Really just want you guys to get these diffie-q methods down and see how they're applied. All right, so a 200 volt electromotive force is applied to an RC series circuit in which the resistance is 1,000 ohms. I know how to say it. It's like on tip of my tongue. We're just going to do is 5 times 10 to the negative 6 for a rod, however you say that, math me. Find the charge Q of t of the capacitor if I of 0 is 0.4. Determine the charge and current at t equals 0.005 seconds. Determine the charge as t goes to infinity. So even though me being transparent myself, I don't know much about circuits at all. They show up applications in math, and typically it's like this where I can just plug them in and solve them. That's where it's going to, the extent in this class is going to be for this stuff, is in your homework. It's going to be set up for you. You plug it in, or you'll be given numbers. You plug it into the equation given, and then you solve it using the diffie-q knowledge you have. You can do this without ever really knowing what we're talking about. So it says RC circuit, series circuit. So that's this equation. So I'm going to write it. R is dq. It's the one right above dt plus 1 over c q equals E of t. Okay, and then we have to grab our variables. Okay, it says the resistance, that's our big R, is 1,000. Our C is 5 times 10 to the negative 6. And then E of t is 200. Remember, E of t is the, where did they state it? E of t, yeah, the impressed voltage E of t. So the voltage is 200, right? So I'm just going to plug this in. Becomes 1,000 dq dt plus, okay, and then I'm going to change this, and then we got to be really careful. This is 10 to the 6. It's dividing, but I'm going to leave that 1/5 like that. Mistake I made when I first worked this is I actually put 5 times 10 to the 6, but that 1/5 is not connected. It's connected to 10 times multiply, but really what this is this is 5 times 10 to the negative 6 is 1 over 5 times 10 to the negative 6. So you would have to really think about what this negative does, and it brings it, 0.0000005, I believe that's it. And then figure out, you see how it's still that 1/5, but times 10 to the 6. Okay. And then that equals our E of t, which is just thankfully a nice, pretty 200, not a variable voltage there. All right. So This is first order linear, so we could take that route. I think that's what I did in mine. Yeah. So, but it's not in the right notation yet. I got to put it in its correct notation. So I'm going to times, this is going to be weird, but it's going to help me out. I'm going to times both sides by 10 to the negative 3. 1000 is 10 to the third, right? So this is just going to cancel it out, but it's going to help me with that middle term with the q. So I get dq dt, and then I get 1/5 times 10 to the third q. And then times 200 times 10 to the negative 3. We could probably figure something out here. 2000 or 200 over 1000, we get 1/5. So I'm going to go ahead and erase all this, and I get 1/5. I'm going to take that nice pretty number. Okay, so that's where we're at now. Now I can come up with mu and do that up here. We're going to run out of room. So mu of t is e, and then it's just going to be that thing 1/5 times 10 to the third. That's a constant t. Right? So knowing my first order linear, d dt is going to be whatever mu was times q. And then don't forget, we got to multiply this side also by mu. Okay, so we're there. I think we could go ahead and change this 1/5 times to the 10 to the third. Let me go ahead and add a new page here so I don't run out of room, not have to write really tiny to fit it all. All right, I think your handwriting's probably smaller than mine, I hope. So I'm going to rewrite, okay, everything comes out. Now 1/5, that's 0.2 times 10 to the third. This is 1/5, right? So if I follow this, this is just move 1, and then 2 more gets me 200. So this is e to the 200t. That's much easier to deal with. Then we're going to have the integral of 1/5 e to the 200t dt. Okay, I'm going to go ahead and do my integral. This is just going to introduce I get e to the 200t back, but if I did the derivative going up, like what I'm about to write down, it's going to introduce a 200. So I need to have 200, 1 over, and it's going to be 1000 e to the 200t plus c. Now, how I did that is I just thought about, okay, if I do the derivative now, I get the e to the 200t, that comes back, but the chain rule introduces a 200. 200 over 1000 gets me to that 1/5 that I initially had. Solving for q of t now. Q of t is 1/1000th plus c times e to the negative 200t. Okay, and then remember that we have I, so if that's q, I of t is just dq dt. So I could take the derivative of what we have there to get to my I, so I can get an initial condition, and then I'll go back. So I of t is the derivative. Okay, derivative of 1/1000th is gone. The derivative of that back is going to be negative 200c e to the negative 200t, right? It's just a chain rule with that e. The reason I did that is if you go back up, they gave me an initial condition, but with I, not with q. So I'm going to use this initial condition now to find the c. I know it's the same c. So once I find c, I can just plug it back in. So 0.4 equals negative 200 c e to the negative, and it's going to be 0. Excuse me. 0 c then is negative 1 over 500. Right? So I of t then is negative, okay, it's going to be negative 2/5 e to the negative 200t. That was plugging in negative 100th to c. Oh, it's going to be a positive too because the negatives cancel. Right? So we have that. Now I know what c is. Right? C is that negative 1/500th. So I can also grab me the q function. I have both now. Q is going to be 1/1000th minus 1/500th e to the negative 200t. So we used I, since they gave me an I condition, I used the I condition. knowing it was the derivative of q to find c, and then I just replaced it. All right, so I have q of t now. Okay, they asked, the original problem asked, I mean, let's go back up and look. It says determine the charge and current at t equals 0.005. So it says both. So I got to do both. So I of 0.005. I'm going to have you guys just trust me if you don't mind. This comes from my calculator, 0.1472. And this is measured in amps. And then Q of 0.05 is 0.003. And then this is, let me spell that correctly. Some measurement of Q. I don't know what is happening up here, why my iPad's being weird. One sec. There we go. This is spelled COULOMBS. Coulombs. I don't, it's something with the, I think is Q the charge. Q is our charge. So that is whatever our charge is measured in. For me, if this was to show up on an assessment, I don't care about the units. All I care about is you setting that diffie up if I give you all that info. You're not required to memorize the diffie Q that was at the very beginning. I would give that to you as a setup. So they asked one more question. They asked for those, and then they said Q, what happens as t goes to infinity? Well, Q is going to go to 1/1000th. We can see that as t goes to infinity, because this being a negative here would force it to go to the bottom, which means the bottom's getting big, I'm making a 0. All right, so there's our 3 answers that they asked for. All right, the next problem is a setup with the other one. So let's go ahead and do that. We have our answers there. So an LR series circuit has a variable inductor with the inductance defined by that piecewise function. That's why it's variable. It changes at 10. Find the current I of t if the resistance is 0.2 ohms, the impressed voltage is 4, and I of 0 is 0. And they said graph I of t. We're not going to do that. You could graph it if you would like at the very end and throw it into Desmos, but I'm not too worried about it. All right, so this is the other series. So let's write down that one. Let me grab it for you from the above so you don't have to scroll back up. It is going to be L times DI, I'm gonna take that times away, DI dt plus RI equals ET. This I is not your imaginary number, right? It's the inductance. All right, so, or actually I is not, Q is the charge, I was the current. L is the inductance. All right, so we have those things. We're just going to plug it in, and that's what it's defined with all that, and then we'll try to solve. This gets a bit tricky because of the piecewise, and then there's just several parts that you can mess up. Okay, L, we're going to focus on just the top first. So we're going to do 1 minus 1/10 t, and then so that was my L, and then di dt plus R. In this case, they told us resistance was 0.2 times I. And then E, they said was 4. So we have to solve this diffie Q. I think right away, I want to get rid of the fraction and the decimal. I'm going to multiply everything by 10. So I get 10 minus t times di dt. That took care of that one. Multiplying by 10 just turns that to a 2, and then that to a 40. Yeah, that's much better to work with. We can look at this. It looks like it is first order linear. So let's put that in the right form, di dt plus 2 over 10 minus t times I. And then on this side, we also get that 40 over 10 minus t. All right, this is definitely first order linear. So I'm going to go up here to find mu. This is e to the integral, or 40 integral of 1 over 10 minus t dt. That's going to be e to the 40, negative 40 of ln 10 minus t. The absolute value. No c on mu, right? Right? We could double check that if you would like with the derivative. That negative 40 goes up to the power, and this is going to result into 10 minus t to the negative 40. I don't think that's what, oh, actually, let's not do that. I think it's separable. Let's go that route. Yeah, forgive me. So you could take that route. What scares me there is that 40. I really don't want to work with the 40th power. Maybe it'll be fine, but I think I'm going to go back and go to try to create a separable. And it's not totally obvious here. So take this line and take that out. Okay, what I'm going to do is we're going to take that 2i and put it to the other side. So first order linear is totally doable here. I just got to it and I'm like, that looks horrible, right? Looks like it was going to get bad. But if I move over here, this is kind of deceptive because that plus, but if I move it over there, I can group these together like that. I didn't do anything but put parentheses around them. And then there you can see that it is actually separable. So we're going to get 1 over 40 minus 2i di, and then we're going to get 1 over 10 minus t dt. There we go. Okay, doing the I part, it is a U sub. The U sub would introduce, I guess we could just do this over here, U equals 40 minus 2i. So du would introduce a negative 2 di. So I know I'm going to have a negative 1/2 ln of 40 minus 2i. It's another absolute value. You could do it with the derivative and you would see that everything cancels out like it should. And then this one, I'm going to get a negative ln of 10 minus t. That's just using another u sub plus c. All right, the powers need to be taken care of. I don't really want to deal with the half because if I take that up, it's going to be a square root. So I'm going to multiply everything by negative 2. So I get ln 40 minus 2i doesn't go in, just negative 2 cancels with the half. Negative with the ln, but now I introduced a 2 to this. And then this constant, I guess we could call it a c1. And then when I multiply it by 2, it's going to become a c. I don't want to do a 2c1. There's no reason to hold that there. Okay, now I can bring that exponent up, the 2. So this becomes ln of 10 minus t squared plus c. Right, now we could take e to both sides. So I'm going to get a 40 minus 2i equals, okay, and then remember if I do an e here, I can split it. I'm going to get a big C. I'm going to call this C2. So I'm going to get e to the ln of 10 minus t squared times e to the C2. That's taking both of them. Remember the plus, I can add those back together to get to the line above. So this gets me a 40 minus t 2i, and then I'm just going to call that C now. And then we know that that ln there also comes down. I guess I could have done that, but I wanted to show you where that was at. So that's what we get there. Remember, I is our function, so I could solve for I, or I could use that to find C. Let's just go ahead and use it to find C. So they gave me an initial condition. They gave me that I of 0 is 0, right? They gave that just directly there at the very end. So if I plug in 0, okay, I get 40 minus 0 equals C times 10 squared. So I get a 40 equals 100C. So C is 0.4. So I get my actual equation in the end, 40 minus 2i equals 0.4 times 10 minus t squared. All right, so there's my equation. Let's see what they asked for. It says find the current I of t with the resistance at and press by that and that. So we found our equation. We are done. You could solve for I of t. I guess we could. It's not hard. So I of t equals, it's going to be a negative 1/2. Let's go ahead and we'll distribute the negative. Okay, so I'll do piece by piece. Let's do I minus 2. I feel like I'm going to lose some of you guys. Negative 40 plus 0.4 times 10 minus t squared. So I of t is going to be, I'm dividing everything by negative 2. I get 20 minus 0.2 times 10 minus t squared. Now, this is for when I is between, or t is between 0 and 10. This changes when it is above 10, because what would happen if we were to go back up, and we're going to just do a little bit off to the side here to get our other part. they said L of t was 0. So this would result in 0 times di dt plus 0.2i equals 4. That results in a 0.2i equals 4, which means I of t in that case, that's a 1/5, so it's 20. Right? I believe. That's just a 1/5. Yeah. So I of t is 20. So our solution then at the very end is going to be I of t is equal to this piecewise function. This is only true. We go back and match what was up there, 0 to 10. And then at 10, we get, what was the other value? 20. So there is our overall solution. I usually leave the number till the end, just because it's easy and I like to finish with that one. I have my big mistake here is I forget to finish the problem and I'll get down to here to the hard part and never consider the other side. So make sure to do that. All right, this is all of 3.1. It is a lot of applications. We'll have this. And then 5.1 is a higher application problem section that we'll get kind of deeper into physics in that section. All right, here's 3.1.